Okay. Good morning, everybody. I'll give you an introduction to the EESSI project, which is our way of trying to keep the P in HPC. How many people here know what HPC stands for? Everybody. Okay. I can skip one slide. So I'm an HPC sysadmin, supercomputing here at Ghent, well, here in Belgium at Ghent University. Been doing open source for quite a while. I like other things beyond open source as well. Usually if you bring me a beer, I'm happy. It's a bit too early for that for now. I've been coming to FOSDEM' for a while. I've been co-organizing the HPC devroom, which is just 2 doors down, since 2014. And I'm the lead developer of the EESSI project and also a core contributor to EESSI. And there's a strong relation between these two. So HPC, everybody knows it. I can skip it. Large computers, parallel computing, expensive servers, lots of CPU cores, maybe some GPUs as well, fast interconnect storage. It's a complex beast, right? And it's not that easy to use as well. So anything we can do to simplify this is actually helpful. What is important that in supercomputers you often see very recent CPUs. Like the vendors will first deliver a first batch of new CPUs to a supercomputer. So you're dealing with the latest stuff. Modern microprocessors support vector instructions, things like AVX, AVX512. You've hopefully heard about these things. On ARM, you have the scalable vector extensions. And using these is quite important for performance. Like if you're not using the vector instructions, or if the binaries you're running are not using vector instructions, it's like you're not using half your PC, or half your CPU, rather. You could be running on a Pentium 4. Might as well. So these things are important because some parts of the hardware are really dedicated to running the parts of the binary that use these vector instructions. So if you're not using them, you're leaving a lot of performance on the table. You're not using a big part of what the CPU supports. So you will be impacted and potentially heavily impacted, especially with scientific software running on supercomputers. There's a flip side as well. If your binaries use vector instructions, and you're running it on a CPU that's a bit older that doesn't support them, it will just crash. You'll get illegal instruction and it will not work at all. So there's this balance between both. But we do in high performance computing, we care a lot about the performance, so we go through the pain of not using these generic binaries that work everywhere. So we want to keep the P in HPC. That means we need to optimize our software for the hardware it's going to run on. So we won't take a random binary from the internet and say this is probably be fine. No, we're going to build our software from source on the host where it's actually going to run. And we're going to tell the compiler, optimize for this CPU that you're seeing right here. So this can be quite important, especially for scientific software. So how important? There's a good example. GROMACS is a molecular dynamics simulation software. So you simulate like molecules and atoms, and that's all I know about GROMACS. Don't ask me more. But I know it consumes a lot of compute. There's some numbers, they've done some statistics. It consumes about 5% of the supercomputing power in Europe. That's a lot, right? 5% is not small, but this is one software package, consuming 5% of everything that's there in Europe. So this is huge. Now with GROMACS, you have to be very careful. What the graph shows here is we're on one system, a fairly recent system, an AMD EPYC Zen 4 that has 192 cores in total. So we're stuck to a single computer. We're running a recent version of GROMACS with a particular input. The details are there, but they're not really too important. And the different graphs show you different GROMACS binaries. So exact same source code, exact same GROMACS version, exact same system. All we did is compile the binary differently. Higher is better, so higher means better performance. If we're using a generic binary on the left, we're essentially using SSE2 instructions, which I think a Pentium 4 20 years ago already supported, so it makes 0 sense. And then you get about 8 nanoseconds of simulated time per day. It's a weird metric, but yeah, it gives you some idea. If we're doing a bit better job, if you say build GROMACS for a more modern CPU, let's say the last decade, anything that supports AVX2 instructions, we already gain a bit. We get to, let's say, 11.5. And if we go full out and really optimize for the CPU we're running on, we get another bump. Now, the difference here is 78%, going from left to right. So if you're not careful and you happen to be on the left, you're losing a lot of performance and you're spending just way more time running your simulations. and you're not using half the hardware that was quite expensive to buy. So that's a bad idea. You don't want to do that. You want to make sure you're on the right side of the graph as much as possible. Now, very good. Why don't we always do that? Well, we try to, but there's a lot of scientific software that gets run on supercomputers, and it's getting worse and worse. It's really expanding to other fields. Bioinformatics is now very compute hungry as well. They have a lot of data. They can start running on GPUs, so supercomputing is very interesting for them. I don't have to explain you about the AI boom that's happening. So that's bringing lots of new software onto supercomputers as well. There's an increased interest in the cloud. So cloud is very flexible. You just spin up VMs, you run something, you tear down the VMs again, and you only pay for what you use essentially. And that's, yeah, supercomputing centers cannot beat that. So it is very interesting. We see other microarchitectures, other CPU families coming beyond Intel and AMD. So for a very long time, it was like everything was Intel. There was nothing else. AMD came back in the game. That was still x86, so it was close enough that it was still easy. But now we have ARM, like the biggest supercomputer in Europe, Jupyter in Germany, just across the border with Belgium, near Aachen. It's full ARM. NVIDIA Grace CPU, so it's all ARM. If your software cannot run on ARM or it cannot compile on ARM, you're not running on the biggest supercomputer in Europe, so that's a shame. So that's already interesting. And then there's the RISC-V CPU family that there was a dev room, I think, yesterday on RISC-V as well. That's coming, so that's a third CPU family, which is totally different from x86 and ARM. So if your software was built for Intel and AMD, it will not run on an ARM, at least not without emulation and other dirty tricks, which only slow things down. Same thing for RISC-V, so you get this huge mess of things, and it's only getting worse and worse. So we're getting more software, we're getting other platforms like cloud, we're getting bigger diversity in CPUs, and it was already pretty bad that we had to build everything from source. On the flip side, the people that help the researchers using the supercomputers, so the support teams, where I am in, they sort of have a cap in the amount of people that can be there. There's only a certain amount of money for staff, but they get a lot more work, a lot more questions, and they need to help a lot more people. So this gives some idea. This is the number of software requests we've been seeing at Ghent University over the years since 2018, and it just line goes up, which is bad, because more requests is more work for us, and it's researchers waiting longer because they can't figure out how to install the software themselves. So that's bad news. Just more and more software, more and more requests coming. Yeah, so this it essentially has doubled in about 5 years, which is pretty bad. So we're constantly busy. We have ideas to improve things, but we just don't have the time to implement the ideas because we're busy handling all the requests. What if we could change that? So what if there's a way that you don't have to install the software anymore that you want to use, even on your laptop, on the supercomputer, in the cloud? What if it was just there, and what if that could be possible without compromising on performance? So that would be interesting, and that's what we're doing with the EESSI project. So that's exactly the goal we have, to really change this situation for the better. So how are we doing this? So EESSI is a bit of a gamed acronym. It's the European Environment for Scientific Software Installations, very long. European actually helps because it helps us getting funding for doing this. You can pronounce it as EESSI, which is funny in titles of talks and stuff. So, yeah. So what it really is a shared repository of installations of scientific software. And I say installations, that's important. It's not a package manager that you can do RPM install. No, it gives you the installation itself. So if you get access to EESSI, the software is there and you can start running it. You don't need to install anything else. And we're really doing this to work together, so we want to avoid all the duplicate work. People were installing software again and again in their own silos, and maybe exchanging ideas or working together on tools like EESSI Build, but they were still doing the actual work of getting things to install and compiled and built in their silos. We also want this to be a uniform way of giving software to the users. So whether you're on your laptop or whether you're on a supercomputer or in the cloud, you should be doing the exact same thing, and it should be working fine. It should work on any Linux operating system. We're still geared towards supercomputers, which are 100% Linux. But you can do virtual machines. I can run it actually on my Mac here as well in a Linux virtual machine, so that's good enough. So we want to support laptops, workstations, supercomputers, clouds, Raspberry Pis as well, why not? support different CPUs. We also take care that we pay attention to the network in these supercomputers. We want to support GPUs to make it even more interesting, next to all the CPU families we already have. And performance is our number one focus point, but we want to automate things. There's lots of software, so we need to automate things as much as possible. We're very serious about testing as well, and of course collaboration is everything we do. Some of this is funded through a Euro HPC Center of Excellence, so the European does really help for getting money to build this out. So yeah, some of this is repetition. Uniform software stack essentially means you have the same software environment everywhere. You go somewhere, either EESSI is already there. If not, you can easily install it. And if it is there, you know what's going on, you know how to use it. We don't want to sacrifice performance. You often see this with like containers and Conda. Somebody gives you container image, like everything is there, trust me, and it works everywhere. It's like, that means you're running binaries that work everywhere, so they're not optimized for my host CPU, so performance is going to be not as good as it could be. I get mobility of compute when I'm sacrificing performance. That's not what we want to do. To some extent, Conda does the same thing. They build one package for x86. They don't build for every possible x86 CPU. We do. We're avoiding duplicate work by working together. We use tools that automate the software installation process, like EasyBuild. But like I already said, you use them in silos. You're not really working together on the installations themselves. That's something we want to change. And it also helps, then it actually opens up additional use cases. So it helps with training. You can give people a temporary supercomputer in the cloud. There's tools for spinning up Slurm clusters in the cloud. You give people access. You give them easy to get access to the software that they want to run on that cluster. You train them on them for like a week. After that week, you throw the cluster away. You literally burn it down. All the VMs are gone. But they can still get the same software environment easy somewhere else, on their laptop, on another supercomputer. So you train them in an environment that they will be familiar with and that they can translate to other platforms as well. So a bit more graphically, what does this all mean? Well, we have a whole bunch of software, like GROMACS, but many other things as well, or Python packages, bioinformatics, PyTorch for AI, whatever you can think of. As long as we have source code and it's open source software, we can install it in easy. Today, that includes 650 different software projects. And then I'm not counting things like NumPy or R libraries. We have, it says over 1,000. It's actually over 2,000 additional things like those. So if you're counting those as software, then it's close to 3,000 unique software projects available today. Works on any Linux system. I haven't seen any exceptions there. Whether you're running Fedora or Ubuntu, I don't care. It works. We support 14 different CPU targets. So today, across essentially 2 CPU families, so AMD Intel is one, ARM is another, and we essentially support multiple generations of CPUs in there. So if there's an AMD Zen 2, Zen 3, Zen 4, we support all of those, and we build the binaries for each of these generations. And then we also already have support for NVIDIA GPUs, also there, 3 generations of GPUs. RISC-V is coming, we're playing with that already. Exploring that, support for AMD GPUs, so for the ROCm ecosystem is a work in progress, so we're expanding our scope as well in terms of what we support. What's really interesting, and I'll show this hands-on, is that the software is streamed in on demand. So once you have access to EESSI, you can see what is there, GROMACS, which versions, whatever. When you then start running GROMACS, it's actually pulling things in behind your back, a bit like you go to Netflix, you pick a movie. The movie is not on your system or on your TV yet. When you start watching it, it's like being pulled in as you watch it. It's the same thing happens with the software here. So things are pulled in on demand. So you're not pulling in a 10 gigabyte container image and then using 100 megabytes of it. No, you're only downloading the 100 megabytes that you're actually going to use. And this is now being embedded in the Euro HPC Federation platform. So we're becoming a rather big thing in Europe across all the European supercomputers. All of this is powered by open source software. So all of this is done in public. Anyone can access EESSI. There's no limitations. You don't have to tell us that you're using it. You just do what's in the documentation. You install and configure ServVMFS, and you get access to everything. The top layer of EESSI, which we call the software layer, is where the actual scientific software is in. So that's the installations installed with EasyBuild, exposed through the module system that we use LMOD for, and there's a small thing that does CPU detection, so you don't have to tell us which CPU you have. We detect it for you, and we do the right things underneath the covers. We use Gentoo Linux to build a middle layer to make things compatible with essentially any Linux system. So we don't care about your Linux distribution, it will work fine. And we use CernVMFS to distribute the software and get this on-demand streaming behavior. Reframe for software testing, Magic Castle to spin up clusters in the cloud, to do demos, or to actually do the builds themselves. We do a lot of the builds in AWS, which are sponsoring EESSI. They just give us free access to whatever CPUs we need to have access to. So everything, essentially, it's one big puzzle. And at some point, all the components were there to actually make the puzzle and build out this bigger thing, fully built with open source software. So same thing, software goes into EESSI. EESSI pops up on local supercomputers like we have in Flanders, the Flemish Supercomputing Center. There's actually one very close here in Zellik, a new one, Sophia, at the Vrije Universiteit Brussels, so the Flemish-speaking university in Brussels. You're now in the French-speaking University of Brussels. They do get along, so you can use it on your laptop, on your PC, as long as you have Linux in there somewhere, in the VM or directly. You can use it in the cloud, commercial clouds, but also this European Open Science Cloud. If you haven't heard about this and you're a researcher that sometimes needs like a small VM to try things, you can get it for free there. Like every citizen in Europe can get a small Linux VM or whatever, where you can do some stuff on. You have like a monthly budget where you can run things. It works on Raspberry Pis. We have done demos on this. It also works on RISC-V boards if you're a bit more careful, if you know what you need to do. And it is on the biggest supercomputers all across Europe thanks to the Federation platform. So we're essentially everywhere. So how does this work? Like I already explained, software is streamed in on demand as it is being used. Thank you, CernVMFS, for that. We built the software, we built the binary so that it's independent of the host operating system. That's where the Gentoo Linux comes in, this middle layer there on the top. We call this sometimes containers without the containing, because containers do essentially the same thing. They build a small operating system in the container image, and then they put you in a box to protect you from the outside world. We actually don't want to be in a box. We want to access the GPU, we want to access the interconnect, we want to get access to all the fancy hardware. So we're taking the idea of being independent of the host, but we're not containing, because we don't actually want to be contained. And we're optimizing for specific CPUs and GPUs as well. We'll auto-detect what you have, so you don't need to care whether you're on an Intel or an ARM system. That's fine, it works fine. As an end user, and this is something we can still improve, we're working on this. Once you get access to EESSI, and I'll try to do a demo if the Wi-Fi holds up. As an end user, you source an init script. This is something I really want to improve. We're working on this. But it does the detection of your CPU, it sets up your environment, and from that point forward, you can just load modules to activate additional software and run the software. And everything will work fine. So once you have access to EESSI, you can stop installing software. Everything is essentially there, if the software that you need is included in EESSI, of course. How does this work? Well, you're this nice person working on her computer. You ask EESSI, do you have the GROMACS binary already? It checks the cache. If it is, then it just runs it. If it's not there, it will download the binary from the mirror server or one of the mirror servers that we have, puts it in the cache, and then runs it. And the mirror server synchronizes with the central server. So we have like a network of servers essentially serving this thing. All of this is done by CernVMFS. We get this for free, essentially. So yeah, the streaming thing is interesting. This gives a bit of a better view of the CernVMFS network. So in the sort of middle of the slide, the darker part is the central server. This is actually sitting in Groningen in the Netherlands currently, one of the partners in the EESSI project. Then we have a couple of mirror servers around. There's one in AWS, again sponsored. Thank you AWS for that. We still have one in Azure, but that one is probably going to die soon. It's sitting in US East, which is not that interesting for people in Europe anyway. There's some people in the UK that built or introduced another mirror server because they like the idea of EESSI, so they want to help the network. And then there's a separate one on the top right that we use to synchronize local mirrors. So that's interesting. If you have an HPC cluster, you actually want to have all the software close to the cluster. So you can actually set up your own mirror server, synchronize with ours, and then you have everything close and you're essentially in full control. You can disconnect the network and everything nicely works. All right, so demo, I'll skip this because I'll do it hands-on. I'll skip this too. Essentially, it's the same thing. You source an init script, you load modules, download an input file for GROMACS in this case, you fire up GROMACS, and it works fine. And you can do the same thing. So this script that I'm showing you, you can copy paste this, put it in a file called easy-demo.sh. If you use Lima, it's a tool for starting Linux containers or Linux VMs, I guess, on Mac OS. So you set up Lima to be aware of Easy, to provide the Easy repository and /cvmfs software easy.io, and then you can run the script. So this script that I showed you works on your laptop. Works exactly the same way on a supercomputer. You log into the supercomputer, you use commands to submit the script as a job, without touching it, without making any changes, works fine. So you get some performance numbers after running Gromax. You log into the cloud, where you may have a Slurm cluster. Here I'm actually, it doesn't show it, but it does show it. So the P equals says I'm submitting this to an ARM partition. Again, I can run the same script, no changes needed. I just S-batch the script and it comes back with the results. And the same thing on one of the supercomputers in Europe, I can do the same thing. So wherever you are, it's fine. If you're a bit smart about writing the script, so if you download essentially the input files that you need, it works fine. The software essentially follows you around wherever you go. So before I do the demo, how do you get access to this? So how do you get this CVMFS software easy.io thing on there? All you need to do is what's on the slide. So this is for a Red Hat-based system. You're essentially installing ServVMFS, so just the yum install or DNF install from a URL. You can find this in the documentation. So this is for the repository where you can get ServVMFS, so then you can install ServVMFS. You configure ServVMFS for, in this case, a single VM or a single client. So you say, just give me a direct connection to the mirror server. If you're a single client, that's okay. And give me 10 gigabytes of disk space at max to download software when I'm running it. So you can limit it as well, and you complete the setup. Run this on a Red Hat-based system, an RPM-based system. You get access to Easy, and it works. Now, you may not believe me, so the best way of showing you is actually doing this. So here I'm in Amazon. I will spin up a VM. I'll make it an ARM one to make it a bit more interesting. We'll have 8 cores, 50 gigabytes of disk, which is way too big. I will launch this. Actually, take a seat. So I will launch this VM. This should be quite quick if all goes well. This gives me an IP address. I can SSH into that IP address. And I'm too fast. Yes, there it goes. This is an entirely new VM. Uptime 0 minutes, so it was really spun up right now. This has like no software. It's a bare bones Red Hat 9, so RHEL 9 operating system. There's not even Vim here, so how can I survive without Vim? No. We don't do Emacs, no. So what I'm going to do, I'll just copy paste here the installation instructions for getting access to Easy. Just literally copy paste for this, the same as was on the slide. I enter this, and now this is going to take hopefully only like a minute. But essentially, all this is doing is the biggest part will be the yum install ServVMFS. Now the nice thing is we don't need to do anything extra. There's actually a second step here as well, which is installing a very small RPM that has the configuration for ServVMFS that knows about Easy. You can actually skip this one because Easy is included in the default configuration for ServVMFS. So the ServVMFS people like us enough that we actually get into their default configuration. Now this is not relying on the Wi-Fi at all to do the installation, so this should be quick. It's literally just installing ServVMFS and its dependencies. So you won't see Gromax, OpenFOAM, TensorFlow, none of this is actually being installed here. So hopefully this completes quite soon. Yes, complete, all right. So now we have ServVMFS available, if I remember the command names. So this is installed, that's actually all we installed. So now you think, oh yeah, we can access Easy, right? So this CVMFS part is now suddenly there, but this looks empty. Like what did I miss? Well, you didn't miss anything. This works like web pages. If you know the URL, you go to it, it auto-mounts the repository, and suddenly it's there. And now, of course, if I do the ls in here, I do see it. All right, so we have access to Easy. Excellent. Now I'm thinking what the best way is to actually do the demo. Well, let's copy-paste the script from the slides like I promised you. This should work. out of the box. So I'll literally put this in a file called easy demo. And of course I don't have I can use VI though, that's okay. Put this in a script, make it executable. Yeah. All right. So just to remind you what the script will do, it will set up our environment for doing CPU detection. What are we running on? Please update my environment so I can start using software. We'll load the GROMACS module, and then we'll just download the file to run GROMACS and actually do the launch. So this spits out a whole bunch of output. Also, again, something I'm not a big fan of right now. The key part here is it has detected that we have an ARM CPU and an ARM Neoverse v1 CPU. So it supports certain instructions. That's the binaries we're going to use. It didn't find any GPUs. That's correct. We don't have any. It does all that. It downloads the input file for GROMACS, and it just runs GROMACS. I don't need to do anything else. So that's excellent. I'll cancel it. This will take a little while. To bring this home a bit more, and since I'm doing quite well on time, I'll download some of the demo scripts as well that we have. Okay. Do I need this? No, actually I don't. What I can do, I mean, Git is in easy, so I don't need to install it anymore. I can just do this. I set up easy to update my current shell to make modules available, so it does the same detection, and now I do have Git. I didn't have to install it at all. So now I can do this git clone of our demo scripts. I have demo scripts here for a bunch of software. It's a bit ugly. I have Bioconductor, Espresso, GROMACS, PyTorch, OpenFOAM, Quantum Espresso, TensorFlow. Somebody pick one? Quantum Espresso. Okay, that's a dangerous one, I think. Let's see what happens. So this looks, wow, science. I have no idea what's going on. But essentially, this will just load modules for GROMACS and then science. So let's run it and see what happens. It sometimes takes a while to react. That's because it's firing up the GROMACS binary or trying it, and ServVMFS says, "Oh wait, I'll get it for you," and then you can run it, right? But it's all transparent, so you don't really notice this. So I don't know what this means, but it's something scientific. It's some kind of plot, I guess, or yeah. So it does work. Okay. So hopefully that was a bit convincing, and the live demo worked. Yes. So that's really all there is to it. There's no hidden tricks here. You can essentially do what I did. If you have access to any Linux system, we have installation instructions for Ubuntu as well. If you get really adventurous, if you're on the RISC-V board, you need to install ServVMFS from source. It's not that difficult. It takes a while. But then, yeah. So the steps may be a little bit different depending on your own system. Now, this is a software performance devroom, right? I already explained you need to make sure you run binaries that are optimized for your hardware. That's very important. So build for your CPUs. Don't sacrifice performance for mobility of compute like people typically do with containers. Now, you can actually build containers that are optimized for specific CPUs as well and run those. And there's actually benefits to that as well. But that's just not what people typically do. They build a container image once and then they drag it along everywhere and they assume everything is magic and fine. It's not, so you do have to be careful. Like I showed you in the demo, another performance aspect, it takes minutes to get access. So in a heartbeat, it works fine. Whatever you're running is streamed in on demand, so you don't need to wait long for it to actually start because you're only downloading what you're using. Again, different from containers. If you have a container image that's big because it has a lot of software, that's good. You have to wait until the whole container is downloaded before you can start running it, so that's a bit annoying. ServVMFS uses lots of caching as well, so if it downloads something once, it has like a local cache, that was that 10 gigabyte I mentioned. So it doesn't download again and again every time you run it, of course. And there's multiple levels of caching in this network. It improves startup performance as well of software on parallel file systems, and that's maybe the last big thing I want to talk about. I have more slides on this. And then humans waste less time as well. We collaborate. We essentially install the software once and easy, and everybody can use it. So the startup performance thing is, I added these slides 10 minutes ago, but So starting software on supercomputers can be slow. Like, what the fuck? It's a supercomputer. Why would it be slow? Well, it's because very often you only have a parallel file system on the supercomputer to like really big things, huge data files, and 100 computers working together on single files and writing things, parallel I/O. Really nice, really bad for software. You don't want to install your software on a parallel file system. If you go to the documentation of like Lustre and GPFS, it actually tells you don't install your software on Lustre. It's a bad fit for what we do. But very often it's the only option you have. And like this, there's nothing else. So software installations are typically small files, binaries, Python files, whatever, and quite a lot of them potentially. And it has a bit of a weird access pattern compared to regular data files as well. You can solve this by putting the software in the container image. Then you have one big file, very good for a parallel file system. But you still want to build your software from source and then put it in a container image. So you like extra work again. And if you're doing a central software stack, so you want to get something rich for your users, doing that with containers is a mess because either you have very big containers or you have 100 of them and people have to pick and it gets very messy again. So one very concrete example, I'll power through this quite quickly. Startup performance, how do we test it? How do we benchmark it? Well, let's try import TensorFlow. It should be fast, right? There's not a lot going on. It's a single import. We're not actually using TensorFlow. Well, this triggers 6,500 open calls. And it opens over 500 directories for some reason. It actually requires almost 3,500 of those files. That includes over 2,000 files from TensorFlow itself, then almost 1,000 files from dependencies and other stuff, and then a little bit of things from essentially the operating system and EESSI, this middle layer, this compatibility layer. In total, it's about 1 gigabyte of data. That's not a lot, but because it's scattered across 3,500 files, it's very bad for parallel file systems. To show this, some benchmarks. This is like the optimal case, crazy mode where you install TensorFlow in memory. Like you actually build TensorFlow from source and you put it in the RAM disk, which is bad because you reboot your computer, it's gone, and you can start again. But this is the best you could do. There's no faster file system than the memory. So if you do that, it takes about 2 seconds to do the import TensorFlow. Not bad. That's worth waiting for. You can probably optimize this. But this is like the ground truth. We cannot really do better than this. More realistic is Lustre. So if you do this on Lustre, so this on the left, it's cold situation. So let's say a fresh reboot. Lustre hasn't cached anything yet. You're the first poor person to do import TensorFlow. You're waiting for over a minute for the import TensorFlow to complete. And this is like normal for Lustre. If you talk to Lustre people, this is like, yeah, it's software. We told you not to do it. If it's hot kernel cache, so everything is cached already, you can get close to the optimal because then essentially everything is already in memory. So Lustre also caches things and it's not actually always that bad as it is on the left. Lustre is open source, parallel file system, very good. GPFS is commercial software. So there you get like 40 seconds, and if it's cached or not, it doesn't really matter too much. So it's always like half a minute to do an import TensorFlow. Very annoying. So bad fit for software. CernVMFS is a lot better, but you have to be careful how you set it up. So with CernVMFS, we get here like in a cold situation, so the caches are clean. You get around 9 seconds if you have the software very close to your system, so a private proxy or a private mirror server. If your mirror server is quite far away, so if you're in the Netherlands and your mirror server is in Dublin, then you're suffering about a minute, but that's as bad as GPFS, so okay. I'm actually downloading from half across Europe, but it's still doing fine. If your mirror server is across Atlantic, then it's very bad. So you have to make sure your network is set up well. And then there's 2 additional situations. There's hot cache, so everything is already in memory, so ground truth or very close to that. If it's not in the kernel cache yet, so not in memory yet, but it is in the private cache of CernVMFS, then you get the stuff on the right. But then we're still talking 4 or 5 seconds, so nothing even close to the 30 seconds or a minute that we were seeing with the parallel file system. That happens because CernVMFS was built for software, right? So it knows the access patterns, it can handle small files quite well. It does local caching on the client, multiple caching levels, so way better than GPFS or Lustre do for this type of stuff. Yeah. More information, time is up, okay. I won't go through this, I covered most of this. Lots of software is already there. If software is missing, this is a community project. You can send us a pull request, please add this. we will check it. If it's okay, we will build it, we will ingest it in EESSI, and it's there for everybody. If you want to learn more about this, come and talk to me. But this is a community project. EESSI is already available all across Europe in the cloud, on the big European systems. There's a list in our documentation. And it is part of the Euro HPC Federation platform, so we're essentially, so Ghent University is being paid to integrate it into this new platform, which doesn't exist yet. It's coming end of March. And it's essentially a one-stop shop, one central point to access European supercomputers. EESSI is going to be part of this. More information on the webinar, and thanks to our sponsors, European Union, European Project, and lots of links to click on and get more information.
I guess we have time for a question.
So if I understood correctly, the main goal of the EESSI project is to make infrastructure, so it's make easy for the scientists to access the HPC, right?
Yeah, to use the software that they want to use, not necessarily HPC, but...
Okay, yeah, so then you mentioned that one issue that you have is making that software performance for specific CPUs, right?
Yeah.
Like ARM, GPUs and so on. So there's another player now coming to the industry, which is the QPUs, right? The quantum processing units.
Yeah.
So my question is there any initiative in your project where to take into account that, or how is that being handled? Because this is a hot topic now in the quantum computing industry. Yep. How can we integrate those things, right? How can you share the load between a GPU or a QPU and so on? It would be very nice to have some open source there in this field, because there are a lot of private things.
So summarized, could EESSI help with the situation where you're getting quantum computers and you want to optimize software for those? Very good question. I don't have good answers there. What I can say is that EESSI is being integrated into this, which is not only the supercomputers, but also the quantum computers. So in some sense, we'll have to provide an answer to that. Now, to me, the libraries that you would use to access the quantum computer is just another software package. I don't care too much. And for me, it's the job of the libraries to make sure that they are able to use the quantum computer very well. Or maybe the compiler that's using, it's not really programming languages in quantum computers, it's very different, but I'm more like on that side, and we will just reinstall all the software that you need to make good use of the quantum computers. But it's not our job, I think, to optimize for, I don't know how a quantum computer works. I'm happy to install thousands of software packages. So as long as it's open source, then yeah, we'll support it.
Okay, thanks a lot.
Yeah. We have to wrap up. If anyone has questions, I'll be outside, so you can meet me there. Thanks a lot.
Thank you.